conversion. So from the literature, it has been observed that the methane conversion around 50 to 100% and CO2 conversion about 25 to 95% can be obtained with the H2 by CO ratio of 1 to 2.5. And the major fact that in the conversion of methane and carbon dioxide, the feed composition, whereas the particle size of nickel is playing an important role, as by increasing or decreasing any composition of the feed can can result in the variation in the results. Where similarly in the particle size of nickel, we require a small particle size of nickel because of the small nickel particle, there will be more dispersion and there will be more good activity of the catalyst. So these are some of my objectives that I have worked on. So firstly, our objective was to develop a catalyst that is suitable catalyst for trireforming. So in this paper, I have synthesized a series of nickel gamma alumina based catalysts with a different nickel loading, that is around 5 and 10%. And we have characterized the catalyst to understand their relation and their physical properties, their relation with their activities. So the nitrogen physios option, that is for the BET surface area, XRD, TPR, that is temperature program reduction. These are the characterization techniques that we have used. And after that, we have tried to optimize the reaction parameters to get the desired H2 by CO ratio of around 1.5 to 2.5. So we can produce like methanol, ethanol, dimethyl ether by the Fischer-Tropsch process. So in this optimization of reaction parameter, we have checked the effect of temperature. So this is my experimental setup. My setup consists of the continuous tubular downflow reactor, and it consists of around 4 gases, that is oxygen, nitrogen, methane and carbon dioxide. And we are feeding water through the feed pump, and we are feeding into vaporizer where it is getting converted into steam. All the 4 gases and the steam is fed into the preheater where it is getting preheated and mixed, then fed into the reactor, and the reactor temperature is controlled by the temperature controllable furnace, and the reactor consists of the catalyst bed where the catalyst is sandwiched within the quartz vule. So the reaction takes place here and it goes downwards into the condenser where the condensable condenses and it goes to the gas liquid separator where the gas is fed to the online GC where we analyzes our products. So this is the pictorial representation of my experimental setup. For the analyst purposes, we have the online GC and it is equipped with the 2 columns. The first is the PoraPack Q column. It is connected with the flame ionization detector that is used to analyze the organic compounds like methane, carbon dioxide, carbon monoxide. And the another column is the molecular sieve that is connected with the thermal conductivity detector that is used to analyze hydrogen, nitrogen and oxygen gas. So these are the some of the formulas that I have used to calculate the methane CO2 conversion and the conversion rate and the H2 by CO ratio. Here the F is the molar flow rate. So moving towards the methodology, this is a scheme, how I have prepared the catalyst. I have synthesized the catalyst by using the wet impregnation method. For the metal, I have used the nickel nitrate hexahydrate metal precursor, which I have dissolved in the distilled water, and after mixing, I put into the alumina support. The mixture is dried in the hot air oven for around 12 hours at the temperature of 110 degrees Celsius, and after the drying it is fed to the muffle furnace for the calcination and it is calcined at 850 degrees Celsius for 5 hours. So here the X percentage nickel gamma alumina X percentage showing the weight percentage of nickel that I have chosen around 5 and 10%. So moving towards the results and discussion. So firstly the nitrogen physics option. This table is showing the surface area, average pore diameter and total pore volume of the support and the catalyst. As we can see, the surface area of gamma alumina is around 134.4, but with the nickel impregnation, its surface area is decreasing. This is due to the blockage of pore and the coverage of the surface of support. And on the right side, there is the isotherm, the figure showing the isotherm. The pink one is of the gamma alumina support, that is showing the type 4 isotherm which with the H2 hysteresis loop, which is depicting the pores of interconnected network. And for the both the catalyst, both the catalysts are showing the type 4 isotherm with H4 hysteresis loop, that is depicting the pores are of slit shape. Moving forward, the X-ray diffraction. In the table, we have calculated the NiL24 average crystallite size by using the Shearer equation, and we found that with the increase in nickel loading, the average crystallite size is increasing. This is due to the agglomeration, that is the formation of larger cluster of nickel particles. And on the right hand side, the XRD profiles have been shown. For the gamma alumina, the marked peaks are showing the hexagonal Al2 through structure, whereas with the nickel loading, we find that the nickel Al2 cubic structure has been found. And in the temperature program reduction, the table is showing the peaks, the temperature the temperature where we are getting the peaks. And on the right hand side, we can see for the gamma alumina, no peaks have been found till 950 degrees Celsius. That is showing that the gamma alumina is has the high thermal stability. It is has a superior thermal stability. Whereas for both the catalysts, we found that there are two peaks, and the peak at the low temperature is showing the reduction of nickel oxide to nickel, whereas the high temperature peak is showing the reduction of nickel Al2O4. And with the increase in nickel loading, we can see the hydrogen consumption is increasing and the temperature is shifting to the right side. This is due to the strengthening of metal support interaction. So this was the characterization. Now moving towards the catalyst activity. So here we have seen the effect of the temperature on the conversion of methane, CO2 and the H2 by CO ratio for both the catalysts. So firstly starting with the methane conversion, as we see for both the catalysts with the increase in temperature, the methane conversion is increasing. As for 10%, its methane conversion is almost equal, constant, but for the 5%, it is increasing. And on the other hand, with the increase in nickel loading, the conversion is decreasing. This is due to the agglomeration of nickel particles, or we have seen the formation of large clusters, which have been verified by the BET data and the XRD data. A similar trend was found in the CO2 conversion, that with the increase in temperature, the conversion is increasing, and with the increase in nickel loading, the conversion is decreasing. This is due to the fact with the increase in nickel loading, the surface area which is available for the catalyst is decreasing. So the conversion is also decreasing. On the other hand, for the H2 by CO ratio, with the increase in temperature, the H2 by CO ratio is decreasing. This is due to the because the H2 by CO ratio mainly depends upon the conversion of H2O, CO2 and the reverse water gas shift reaction. And at high temperature, all these reactions are predominant. So what is happening at high temperature, the produced hydrogen is getting utilized. It is reacting with the carbon dioxide to produce carbon monoxide. So our H2 by CO ratio is decreasing. So the comparison. So in last, I have compared the work we have done with the papers that have been already published. So I found that we have also calculated the conversion in the form of conversion rate to compare it with the paper, the Kumar et al. 2019. So we observed that the conversion rate we observed is more than what they have published. Our H2 by CO ratio is less than their H2 by CO ratio. This can be due to two facts. Firstly, the alumina. The alumina they have chosen is of acidic nature, whereas what we have chosen is of basic nature. And other thing is that their feed composition is entirely different than ours, because like I have already told, because of the feed composition, our conversion and H2PO ratio can drastically change. So these are the two major things that are depicting that our results are different from them. So after the comparison, this is the summary of my paper. So we have synthesized the nickel gamma alumina catalyst by using wet impregnation technique, and we have characterized the catalyst with nitrogen physiosorption, XRD and TPR, and we have calculated or evaluated the catalyst activity at the temperature range of 700 to 800 at atmospheric, and we observed from comparing both the catalyst 5% nickel alumina and 10% nickel alumina, we observed the 5% nickel alumina showed better activity than the 10% nickel alumina. So we thought the performance of this catalyst is revealing that this type of catalyst, that is nickel alumina based catalyst, can be suitable for producing the syngas via trireform. So thank you. That's all from my side.
Thank you for the excellent presentation. So it's a very excellent work. I think it is one of the most sought after research area nowadays and very important topic. But I just want to have one question before it is open to the floor.
Yes, sir.
Why this nitrogen is being put in? Because when commercially we do syngas, I think people try to avoid nitrogen. But in your feed, why you are giving nitrogen? That's not clear
Yes,
to
sir.
me. Can you just
Yes, sir.
explain?
Yes, sure, sir. Sir, nitrogen here it is acting as an inert. We are putting it as an inert because for the analyzing purposes, we have to analyze the how much we have feeding the feed in the in the we are analyzing in the GC. So our nitrogen is constant. It will not react with any of the gases. So we are using it for finding how much moles it is we are feeding and how much moles we are getting. So it is just for the analyzing purposes we are using the nitrogen gas.
Oh, okay, thank you. Any more question? Any more question?
So, there is no question.
Okay, then we can switch over to the next speaker. Who is the next speaker?
So, we have a question. Can you hear me?
I can't hear you. Unless you close the mic.
সোমদা একটা কোশ্চেন ছিল
You can speak. I cannot hear actually properly. Yes, yes, go ahead. Please go ahead. Please go ahead.
ফোন নাম্বার
Ms. Sharma, please answer the question. Hello.
yeah the question is have you compared the steam to carbon ratio as such with your things as well as what Somonda asked with the nitrogen you will have the NOx formation in your in the product because you cannot control NOx formation if you have nitrogen and the temperature. So
I think she has discontinued the microphone. Now the microphone is on. Okay, okay. So
So we
can you
haven't
answer,
checked.
please?
So yes, sir. So we haven't checked yet the steam to carbon ratio yet, but for the question around the nitrogen, like right now we are just focusing like we are taking it as an inert gas. So we are not taking into consideration like the around what you were saying about the NOx formation. We have not taken that thing into consideration.
Yeah, that is one as well as what about the steam to carbon ratio compared to the conventional steam to methane reforming? Is it different?
Sorry, sir.
For steam to carbon ratio that we use in the conventional steam methane reforming and here what are you doing? Do you have those parameters?
Yes, sir. So in this, we are using a very low amount of steam in our dry reforming of methane. Comparative to the steam methane reforming, as because I've already told like there are different type because of the feed composition. If any feed like if as both the oxygen and water are their oxidizing agents, and if their composition is very high, those reactions will predominate and the uh, other will reduce. So we have to maintain a feed composition in such a way that we are our CO2 is also our dry reforming reaction is also taking place, so that its conversion is also higher.
Okay. Any more questions, please? Thank you.
Thank you, sir.
Thank you. Thank you. Shall we proceed to the next presenter, please?
Yes, Sonda, we can proceed. I think this one of
Who is ready?
you are mute, yes. So, should I share this slide or you will do this?
Sir, I am sharing from here.
Okay, no problem.
Oh, look. Okay. Electrochemical processes, separation techniques. Please go ahead with your presentation.
That is my presentation is visible?
Yes, as far as I am concerned, yes.
Yes.
Your audibility is also good.
Okay. Good afternoon, everybody. I am honored to present the review to redefine wastewater as the resources for nutrients, precursors, different starch element, and fertilizers, and other products also, and prospect of electrochemical process induced separation techniques for the same. These are the outlines of my talk. A brief introduction. Just a minute. Sorry, sir. I'm extremely sorry, sir. Actually, অন্য একটা presentation খুলে গেছিল. I am extremely sorry. Okay. Good afternoon, everybody. I am honored to present the review to redefine wastewater as the resources for several nutrients, precursors, fertilizers, and other value-added products, and the prospect of electrochemical process-induced separation techniques for the same. These are the outlines of my talk. A brief introduction, resources available in wastewater, methods of resources mining, commonly used methods for resources recovery from wastewater, prospect of electrochemical techniques for recovering the resources from wastewater, conclusion and future outlook, and references. We all know, due to increasing rate of population growth in the urban areas and rapid industrialization in 20th and 21st centuries, billion tons of industrial, municipal, and agro-industrial waste are being generated per annum, which has adverse impact on natural resources and living beings. In this context, and for celebrating 150th birthday of Mendeleev's periodic table on 2019, European Chemical Society presented a special format of the periodic table to describe and indicate the scarcity of element and subsequent potential threat. The area occupied by each element gives an indication of the amount of element in the earth crust and atmosphere. It is also to indicate that special effort must be given to minimize the waste generation and partial recycling. Otherwise, a few natural elements which are highly important and critical for our surroundings world may be diminished. Therefore, focus should be given on the development of new techniques and modification of existing methods to enable the use of these resources, elements, and materials in a circular way. In 2015, Stephen and others classified the waste problems into 9 major planetary boundaries based on their adverse effect on the living beings, such as climatic change, ozone layer depletion, acidification of seawater, decrease in biodiversity, etc. Unfortunately, important sustainability targets are being pushed beyond the tolerable limit due to human activities. Carbon, phosphorus, nitrogen are the 3 key biogenic elements among the most important 6 biogenic elements for the living organisms as the primary constituents. However, the generated waste materials are enriched with carbon, phosphorus, and nitrogen, in the form of carbon dioxide and methane, ammonia, and different phosphates. Ammonia and phosphates are highly important from the agricultural point of view, but these are being discharged into the wastewater stream directly. This causes the eutrophication and several adverse effects into aquatic life also. Also, waste materials generating in industries and municipalities before or after its treatment are mixed with the water used for cleaning purposes, and the stream are being discharged. So water is one of the most adversely affected natural resources. According to the latest CPCB data, rate of sewage generation in India is 72,368 million liters per day. Approximately 50% of which are being generated by 5 states: Maharashtra, Uttar Pradesh, Tamil Nadu, West Bengal, and Gujarat. Several scientific reports also inform that world water consumption may increase by 20 to 40% from the present water consumption in next 3 decades. So there is a necessity to reuse and recycle of used water to handle wastewater in the water management cycle. Also, because of diverse source of generation, varieties of components are present in wastewater streams as the contaminants such as different biological bodies, fertilizers, nutrients, and precursors. Recovery of these items during the wastewater treatment may be helpful to use the resources in a circular way and may lead to a circular economy, the principle of which are to decrease the consumption of raw and input materials, to remove the waste from waste materials or resources or substances as much as possible, so that the remaining substances can be recovered for elemental balance and reutilization of resources, and to contribute for achieving global sustainability targets on water and sanitation significantly. Moreover, recovery of these resources in addition to energy production in wastewater treatment plants may be helpful to reduce the cost of wastewater treatment and the elemental scarcity also, which may be helpful to take a step towards circular economy. The commonly used resources, the commonly available resources in wastewater are energy and biogas, nitrogen and phosphorus, nutrient-based fertilizers, strategic elements like gold, silver, copper, and heavy metals like nickel, cadmium, zinc, phenols and its derivatives, sulfates and sulfides, biological proteins and lipids, and different value-added products. These are the commonly used resources mining techniques: physicochemical techniques, chemical methods, biological methods, and electrochemical techniques. The commonly used techniques are ion exchange followed by adsorption process, which is mainly used for nitrogen recovery as ammonium and phosphate recovery, phosphorus recovery as phosphate. Stripping and adsorption, which is primarily applicable for nitrogen recovery as ammonia, in which pH was observed to have influence in NH3 stripping kinetics, and in some studies it was reported that the optimum pH for stripping must be greater than 9.5. Gas permeable membrane, this is also mainly for ammonia recovery, in which approximately 95% or more ammonia recovery can be possible as per the reported data. Magnetic microsorbents, which is mainly used for P nutrient recovery. Chemical precipitation, also useful for P nutrient recovery. Struvite precipitation, in which P recovery as well as nitrogen recovery as ammonium is also possible. In this, magnesium 2+ plays the role of limiting reagent, and the solution with phosphate and ammonium ion can lead to struvite precipitation. Otherwise, ammonium should be added from the outside also. Biological phosphorus recovery, which is also mainly for phosphorus recovery. Algae harvesting, in which P content in dry algal biomass can be achieved up to 3.4%. And some direct conversion methods are also available to directly convert these waste material into useful resources, such as by growing edible plants to extract plant proteins, by converting to several protein-rich food sources such as single-cell proteins and others, which may be used as feed for the fish and aquatic creatures. Although these commonly methods have several advantages, they have several limitations also. Most of these methods limited by external chemical addition, heavy metal leaching, presence of toxin in the final products, high energy requirement, adjustment and necessity of adjustment and control of pH, high operating cost, and sometimes post-processing may be needed. To overcome these issues, nowadays scientists are searching for some other techniques for recovering the resources from wastewater, and electrochemical techniques are found to be promising because this facilitates multi-analyte handling capability, low instrumentation cost, less consumables are required, input energy is low. These are potential for on-site analysis also, and sometimes this can facilitate the scope for indirect biosensing with high sensitivity and low detection limit. These are the commonly available resources which can be mined from wastewater using electrochemical techniques. But before using electrochemical technique, one should focus on these points, that is, which materials need to be recovered, which electrode materials and electrochemical technique need to be employed, what are the operating condition, and which electrochemical parameters are the controlling parameter, whether there is any necessity of integration of other techniques, and selectivity of the used electrode material towards the target analyte. Among the different types of electrochemical technique, capacitive deionization is gaining importance in the wastewater treatment sector for the desalination and softening of water by removing charged particle. Ions and charged particles present in a wastewater stream can be separated by generating an electric field between the two closely assembled electrodes. In this technique, a voltage bias is applied to polarize the non-Faradic electrodes. Due to that, ions transport to and stored capacitively in the electrical double layers on the porous surface of the electrodes. Anions are adsorbed on the positive electrode and cations are adsorbed on the negative electrode during the charging step. During the discharging step, ions are released back to the bulk solution when the voltage is released or reversed. Although high voltage facilitates the thicker electrical double layer formation as well as movement of charged particle or ions towards the counter electrode with a faster rate, in capacitive deionization, low potential window is generally applied for restricting the generation of Faradic current. This requires the low energy also as compared to other desalination process. To avoid co-ion expulsion, sometimes ion exchange membranes are used in CDI cells. It is reported in few studies that integrating with ion exchange method, membrane-based capacitive deionization can mine more than 65% ammonium as the N nutrient and more than 40% phosphates as P nutrient. Therefore, this method on integrating with suitable separation technique can efficiently separate charged nutrients and help to recover maximum nutrient in addition to reducing salinity in view of circular economy. Moreover, CDI method has been implemented in different studies for nitrogen recovery as ammonium. Ammonium along with other positively charged ions first transport through the ion exchange membrane and adsorbed in the activated carbon-based cathode, where ammonium ion deprotonates and converts to aqueous ammonia. It is then expected to be trapped in or within the cathode, resulting ammonia-rich solution due to the deprotonation of the ammonium ion via Faradic reaction. The constantly charged positive ions like potassium, sodium, and calcium are largely released back into the waste stream because of polarity reversal. Recovery of ammonia has also been studied from various wastewater streams, coal gasification, grey water, and others. Electrode K2Ti2O5 activated carbon mixture based showed an approximate 80% ammonia recovery. In FCDI cell, both phosphorus and chloride will be moved across the ion exchange membrane also, and by which we can recover the P nutrients as phosphate rich solution also. C nutrients as oxalate, acetate and formic acid, iodine and bromine are also being reported in several studies as the recovery product from wastewater using capacitive deionization method. Some toxic metals like arsenic, mercury, copper, zinc, etc. are also being recovered as reported in several studies. Electrochemical redox processes are also very useful for resources recovery. Redox reaction driven conversion of the central element of the target into a separate oxidation state may lead to effective and selective separation. The oxidation reaction occurs on anode either by facilitating the electron transfer directly between the reductants and anode, that is in case of direct electrochemical oxidation, or by generating the in situ oxidation species, that is in case of indirect electrochemical oxidation. The electrochemical reduction employed for the wastewater treatment purposes, where the electron generated in anodic reaction or supplied by externally are being consumed at the cathodic reduction reaction. By employing electrochemical reduction in wastewater, metals are recovered from free metal ions, nitrate and nitrites are converted to ammonium, and reusable scarce and abundant heavy metals like copper, tellurium, silver, uranium, nickel, zinc, etc. can also be recovered, as reported in several studies. In few studies, experiments were successfully conducted showing phosphorus and N nutrient recovery as ammonia-rich solution and phosphates or phosphoric acid-rich solution, sulfur as elemental sulfur and sulfur derivatives, bromine and brominated products as the recovery product from wastewater resources. Next commonly used method is electrochemical stripping analysis. This is with or without integrating with other suitable units has been extensively used for the recovery of different resources from the wastewater generating from diverse sources. It has several advantages such as multi-analyte capability, low instrumentation cost, less consumables, low input energy, etc. The method is a combination of electrodialysis modified with stripping, either membrane or acid stripping. In this process, a pre-concentration step of the target molecule or substances is coupled with a stripping technique. The pre-concentration step is operated and controlled by a suitable electrode. The concentrated solution is then used for stripping purposes electrochemically. Tarpe et al. And Liu et al. Reported approximately 93% and greater than 63% nitrogen recovery respectively, in which cation exchange membrane was used to separate the anode and cathode. Based on mechanism involved, it is suitable for N nutrient recovery as the ammonium. However, and also coupling with acid adsorption, electrochemical stripping has been successfully used to recover N nutrient as reported in different studies. Katke et al. In 2016 reported in their study an approximately 95% N nutrient recovery as ammonium. One of the most promising technique for resources is electrochemically induced precipitation, like chemical precipitation and struvite precipitation occurring in case of chemical method when we are operating chemical methods. It is found to be promising for P nutrient recovery mainly in the form of phosphate, and when simultaneous P and N recovery is needed, the recovery product may be struvite. Integrated with some other methods, it is used widely for P nutrient as well as struvite recovery simultaneously. In this process, when an external potential bias is applied, suitable dissolved substances present in wastewater can undergo chemical reaction and form some insoluble precipitates. Because of the applied bias, water splitting can be occurred generating hydroxide ions, which are essential for the precipitation. The thus formed precipitates can be separated out from the wastewater. Kappel et al. Reported approximately 70 to 95% phosphate recovery from the municipal wastewater using steel plate as cathode. Lee et al. Reported a maximum of 92% recovery of phosphorus using a platinum coated titanium based anode and titanium plate as cathode. Pereira et al. Showed more than 94% phosphorus recovery from septic tank effluent. Recovery of P nutrient along with N nutrient as struvite was also reported in several studies. Wang et al. In their studies reported in 2019 reported a recovery of P nutrient approximately 99.51 to 97.69% after dosing plant S and magnesium metal from actual wastewater. Seed et al. In 2018 reported approximately 80% P nutrient recovery as hydroxyapatite. Approximately 99% phosphorus nutrient and greater than 90% ammonium recovery was also reported in some studies. Rare earth metal were also observed to be captured by the hydroxide ion as metal hydroxide, and it can undergo dehydration to form their stable metal oxide. Considering the above mechanisms, O'Connor et al. Reported a study with CNT-based filters showing the capture of europium, gadolinium, neodymium, and scandium as their oxides via electrochemically induced precipitation method. One of the other promising electrochemical technique is electrocoagulation, which is useful for treatment of inorganic, organic, and pathogenic contaminants and is applicable to treat urban, domestic, and municipal wastewater. In this process, a metal is added to the wastewater under treatment to form in situ metal oxide electrochemically. Firstly, direct current is applied on the electrodes dipped into the electrolytes. The thus formed metal oxides are destabilized and aggregate precipitates and particles. These also adsorb the contaminants present in the solution in dissolved state. Earlier, phosphorus was recovered via electrocoagulation using magnesium, aluminium, and iron, as reported in several studies. However, in 2002, Zhu et al. Reported a recovery of byproduct from simulated egg processing wastewater and egg processing plant wastewater. The byproducts recovered are threonine, valine, leucine, isoleucine, phenylalanine, and lysine, that is different kinds of amino acid which are commonly present in natural egg. Integrating with chemical leaching, thermal process, and other suitable processes, various heavy metals can also be recovered from the electrocoagulation sludge. Garcia and Carrillo in 2019 reported a study in which they used an aluminum electrode to recover gold and silver. Gajda et al. In 2017 showed a high percentage of heavy metal recovery, that is iron, copper, and zinc, in a microbial fuel cell. Uranium removal and recovery, approximately 89.71%, was also reported in a study. Metal can also be recovered in its hydroxide form. In a study, hydrogen recovery was also reported.
Mr. Boiragi, please control your time. You are overspending the time. Please restrict your
2 to 3 minutes.
presentation.
2 to 3 minutes, sir. Okay. So another suitable method is electrolysis or microbial electrolysis, in which we all know bioelectrochemical system is the one of the newest and promising bioenergy technology for the simultaneous wastewater recovery and energy production. However, microbial fuel cell is uncompetitive in comparison with other energy sources based on the economic and environmental values. Microbial electrolysis cell deals with hydrogen energy production via an external electric supply, and this also facilitates recovery of various resources from wastewater. MEC have several advantages such as production of hydrogen from various organic substances, dark fermentation byproduct, low energy input, etc. And as for electrode material, Lee et al. Reported stainless steel plate cathode and some other electrode in an electrolysis cell and showed a 53% potassium recovery and approximately 99% of phosphate recovery. Blackwedge and others in 2019 reported a study performed with 4 parallel frame based BES reactor in which they showed approximately 92.9 to 94% sulfate removal and recovery. One ethyl showed approximately 40% efficiency of dissimilatory nitrate reduction to ammonia as the recovery product. With this, I wish to conclude the study. Reclamation of the different resources from wastewater in view of circular economy is discussed in this review. Prospect of electrochemical techniques to recover various resources is described. The commonly recoverable resources from wastewater are nutrients, natural and synthetic resources, heavy metals, different scarce element, different valuated products. The methods requires low instrumentation cost, less consumables, and low input energy, and are potential for on-site analysis. Wastewater generating from diverse sources can be mined to reduce the deficiency of nutrients and precursor in addition to energy recovery and water recycling. And with this, I can conclude this review discuss the necessity of redefining wastewater stream as the resources for different nutrients, precursors, fertilizers, and other valuated products, and the requirements for moving towards circular economy from the existing linear economy and mixed economy. These are the references I followed. And with this,
Thank you
all for your kind and generous
all.
attention.
Thank you for this nice presentation, nice review actually. Any questions on this? I have, in case there is no question, I have just one question for Mr. Vaidagi.
Yes, sir.
You have been only telling the percentage of recovery, etc. But what about the biofilm formation on the electrodes? I think this is waste material when a continuous operation of electrochemical extraction and separation. I think the biofilm is a big problem to tackle. So have you addressed that issue, or is anybody addressing? Because the commercial system, there should be, the results may be totally different than what you are presenting here.
That is basically a very challenging task, and that is only the limiting factor nowadays for implementing the electrochemical technique for resource recovery. Am I audible?
Yeah, are you audible there? Because the gas sound is disturbing.
Some studies, they use some materials and chemicals in this solution so that after some time, the biofilm can be degraded by using reverse potential method. And in case of electrochemical sensors also, you see they are generally regeneration step is taking place. We are using a regeneration step after a certain time or after certain use basically, so that the surface poisoning can be avoided and the surface can be remediated.
So in situ something cannot be done to reduce the biofilm formation on the electrode,
Yes, sir.
rather than adding chemicals.
Yes, sir. So nowadays, people are using different metal nanoparticles so that selective metal nanoparticles basically, which are specific to target analysis and which avoid the formation of biofilm, which restrict the formation of biofilm and restriction of agglomeration of other waste material apart from target materials on the electrode surface.
Okay. Thank you very much, Mr. Vaidagi. Let us have second last presentation of this session. Please, once the presentation starts, please discontinue the DAS microphone. Please switch off the microphone on the dial.
Should I start? Yeah. Okay. So good afternoon, all of you. So I am Devi Bhandari, alumnus of 2008 batch. Now I am working as an assistant professor in the Department of Chemical Engineering, IIT.
Mr. Vandari, you are not audible. Mr. Vandari, you are not audible.
Yeah, I am on the diet, but I have to check whether there is a problem. Am I audible now? Right, please. Okay. So again, this is that. So this is what I was so this is part of the big work done by one of the students, yes, so we are in a competition marketing lab for technical science. So competition marketing, of course, you know all microscope, right? So competition marketing is used on the management solution, and so that's our goal. Okay, so a brief introduction like what we are going to do today. As you have seen in the title, that is the process of doing rational nanosystems, right? So we know how this nanoparticle is in the solution, and we are trying to understand that very basic of multi-elemental nanoparticles. So in that way, how to do solution. So why is the main problem? So here it is what is called multi-elemental nanoparticles. So this where the particles are more than
Mr. Vandari, please start your microphone.
audible now?
Really, yeah, it is audible. Why it is not able to hear again?
Is it audible now?
Hello.
Oh, yes. Yes, yes.
Hello.
Yes, can you?
Okay, should I continue now? Uh, yes.
Go ahead.
Go ahead.
Sonda, is it audible?
Am I audible?
Hello?
Am I audible?
You're audible now. Dial get close, then we can hear you.
Okay. So yes. So we are talking about polyelemental nanoparticles, which constitute where the number of constituent elements are more than 4 or 5. So
Please
these kind
switch off the microphone. Oh, okay.
yeah, this is what I mean. You can start with one. Okay. So yes. So these are the kind of arrangement of elements can take place in case of this kind of nanoparticle. It can be made glass, which is completely a mixture, amorphous solid. And then it can be of alloy kind, it can be intermediate, so 2, 3 metals are interconnected with each other, like in their interstitial phases. This can be a multi-phases, and this is a portion one. So this is very common. Now, why is the problem? So let's see where are the applications. So these are the broad range of applications where this kind of nanoparticles can be applied. Okay, where it can be utilized because it has all the properties. You will have properties of 5 different metals. Like one is maybe sensitive to photocatalytic activity, one may be sensitive to some biodegradation activity, one can be used for the sensor technology. So all of these can be used up together, and you can make the combination of all these properties. Okay? And of course, like what we are trying to understand is the manufacturing or the preparation process. So here, these are the typical preparation process which we will use. We will have seen in the literature. And what is the main drawback of all these processes is that we call it as a high entropy alloys. Okay. And to carry on this high entropy alloy or to manufacture this high entropy alloy, you need to have a lot of energy on it. So that's why you can see the this is thermal shock method where you have to put it in a very high temperature, 1600, 1700 Kelvin temperature, and then you are quenching it out. So you need a lot of energy, right? So and what we are trying to do in the lab is we are trying to understand it through the simulation that can we do it in a solution phase. Simple solution phase using self-assembly. Self-assembly represents what we are saying is surfactants mainly. So can we use okay, and this self-assembly will all these definitions of simultaneous agglomeration with dual delta G. Delta G should be negative and it should be a non-covalent interaction. That means there is no bonded interaction. We are talking about only the physical interactions, right? And of course, this self-assembly has found tremendous application in all of these drug delivery, in imaging technology, in catalysis sensors. All these applications has been people have reported their work in developing all this technology, right? So here, what our goal is, can we take a solution? Let's say we are having one kind of nanoparticle where you can put a surfactant to elevate its size, right? And then we are trying to grow another another part of a nanoparticle or another part of another part with different element using its own precursor. And there we will use a different kind of surfactant so that it can behave or it can capture according to that their interaction with that kind of surfactant. So that's what the goal is. So in order to do that, what we need to first understand is that how this nucleation growth occurs in a solution. So nucleation growth is fine that whenever we are doing the reduction, the individual atoms will generate in the solution, they will agglomerate to form a nucleate, and then that nucleate has to be of certain size, critical radius, then only it will grow, otherwise it will dissolve back again. Right, so that is again the surface energy phenomenon that we all right. So that is what our cross nucleation theory is, where we see that it is it can be also primary method, where the nucleates which are below the critical radius will get dissolved and form a larger nucleate, larger nanoparticle. And inequalities where you can have different sizes of nucleate which will not meet each other and will grow. So that is the one. Again, the examples are of this kind. And then why we are using like gold is not very precious for ornaments. Gold is very precious for our its effect on our biological system. For generations, gold has been used as a medicine. In old age Ayurveda, they used to grind it to create the gold nanoparticles. It's okay. The sciences maybe that same technology was not there, but they could know that okay, with this much of grinding or with this much of preparation, one can get nanoparticles of certain size and shape. So that's what we will use. So here we are using gold nanoparticle because again it's easy to handle. Okay, we are professional scientists, so we don't need to bother about buying gold from a gold seller, right? So we can create any of the precious metal ever had, and we can make it in a computer, right? So only thing we need some data. That's it. Okay, so here how these gold particles can be generated in the solution. Here the ions, gold ions will be reduced to the atoms and then atoms will create the nuclei. So this is a typical time frame of 200 microseconds, right? And again these nucleates will polycize with each other and will grow to that takes place around 200 microseconds. Okay. And or it can be another phenomenon where you have put the surfactants. So surfactants will individually bind these ions of these metal atoms, and then they will grow. So that is another way to precisely define the size and shape of the nanoparticle. And electrochemical process, of course, you are having the ions, micelles, and then you are reducing the ions to form the nanoparticle inside that micelle. Okay. So now here, this is a very interesting area because what we are trying to see that the nanoparticles which have been generated here. Can we do it outside this? Like can we form this agglomeration on like not inside the micelle? Because whenever it is going inside the micelle, it is becoming inert. Like it cannot grow beyond a certain size. So here we are trying to see that can we form these type of micelles outside of the micelle, and so that it can directly get adhered to the other surface of the nanoparticle. Okay. So so now in order to do that, what we are doing, we will create the micelles. We will create the micelle in the solution, like water. We will take as a C-cap micelle, C-cap surfactant, and we will dissolve it in water. It will form the micelle. So what we need, we have a surfactant and we need a force field. So what is force field? Is that how each and every particle of each and every constituent atom of a micelle will behave with the other particles. Other particle in the sense you have water in the system, you have other surfactant molecules in the system. So there are two kinds of interaction. One is with each and every surfactant and with water. Right? So each surfactant with each other will have the same potential, same forces, where the bonded interactions are like two kind of interaction. One is non-bonded and bonded. Non-bonded interaction have charge and van der Waals. So charges are opposed by the Coulomb law, and the van der Waals interaction is described by Lennard-Jones potential. So Lennard-Jones potential, and we have this SPCE model for water. Okay, let's take it as a name. Don't go into the details of what is the model. But what we have here in SPCE model is we have a 4 oxygen and 2 hydrogens are coming out of it. Hydrogens are massless, charged, only it has charge, and water has both mass and charge. And of course the non-bonded interactions. Right? And so we create this kind of micelle. So water is removed for the clarity so that you can see the micelle. Here you can see this is the cyan color is the core of a micelle, and this pink, we call it pink. The pink color is the head group, which is C-tap, so the ammonium group, and the brown is basically the bromide ion, which is moving in the periphery of this ion. Okay. So now we are what we are going to do, because this is a very core material for us. Like how the surfactants are behaving is very core to us. And if the surfactant behavior is not really up to the mark, then we should reconsider whatever models we have taken. Okay. So now again, just for the students mainly, what is molecular simulation? We are fighting, like every atoms are fighting with each other, so they will have a net force on each other, and because of that force, Newton's law of motion, how much displacement can take place, what will be the change in the velocity, what will be the change in the position, so that will be updated with time, with respect to time. Okay, all these simulations are in order of femtosecond. We run all these steps for 10 to the power 6 to 10 to the power 7, 8, depends on whatever the system. So it will be the simulation results will be in the order of nanoseconds, or maybe hundreds of nanoseconds. Okay. So here in the micelle, we have to characterize the micelle. So here the 3 plots to characterize the behavior of the micelle. Here you can see that this is the density profile. So this ammonium group, the N is for the ammonium group. This blue is for the CH3 or CH2, the alkyl chain, and this is the water. H2O is the peak line. So here you can see that ammonia is the end of the cationic part. So that is around 0.25 nanometers of size. So which is very well accepted in the literature. So we are going ahead with the system. And this is the radial density function or distribution function, which is directly gives us this data actually. This is the point where radial distribution function and the experimental data can be matched together. Like the Newton diffraction data of this same system will exactly matches with the RDO, with the radial distribution function. So this is again this exactly matches with the literature data, whatever is available. And the change in the temperature to ensure that it is not it is also behaved similarly with respect to the temperature as well. But for our cases, we are not varying any temperature; it's only at the single temperature. Okay. So now this is the kind of system. So this is the gold surface of the, you can think about it, this is the gold nanoparticle, a larger gold nanoparticle surface, which is, we can say, for simplicity, we can think as a completely flat surface. Ideally, it should have a flat surface, but for the simplicity of the competition experiment, we took it a flat surface. Let the micelle go first. Let the micelle be stable on the surface. Let us see that where the particles are getting accumulated. Then we will extrapolate to the like for a curved surface or a plain nanoparticle. Okay. So here you characterize this system. Here you can see that this is at zero position is basically on the top of the surface, and here this is the density profile of different like different parts of the surfactant and water. So here you can see that this is the zone where surfactants are lying. And here in the dynamics you can see also that it is staying here very much close to the surface. So now what we see that this bromide molecule, bromide atoms or ions are moving around, right? So the question is, if it is moving around, then the charge could be an issue, like how the charge distribution is taking place, right? So here we carried out, we calculated the charge distribution also of this cross section, like along the x direction. Okay. So here you can see that the negative and positive like anions and cations charge distribution, but overall charge distribution is in this zone is of little bit of negatively charged, like very faint, but there is a negatively charged. So that is where we are trying to see that can we drag ions or reduced atoms to get deposited on this surface. Okay. So we carried out a number of simulations with different configurations, but it did not appear to be depositing on the surface. Okay. So what we did then we calculated the PMF. So PMF is essentially tells us about that how much is the energy barrier for the process. Like if we are dragging from one particle or one node at here to the surface, how much energy do we need or we gain some energy. Right? So delta G is whether delta G is positive or negative. So that is the simple question we will answer. So we took the understanding and we did this analysis, and here we see that as the ions or the atoms are approaching the surface, it is getting very difficult for it to reach here. Right? And then there is again a sharp energy barrier which falls very sharp. Right? So in order to achieve here, you have to rise here to this point, which is approximately the value of 10, and here it is also approximately the value of 10. Like it's not. So overall, what we see that we need to put some energy. Overall, the net energy is positive. So we have to put some energy. So now our goal is how can we reduce it? We tried with salt, we tried with few other compositions also, different materials also, different surfactant also. But this barrier is very steep, and we are not able to again we don't know how to approach from here. We have to find the path. Okay. So what the conclusion we can get is that the energy required is we know that how much we have to apply, so that can be applied, but what we want that the process should be spontaneous. We can do it spontaneously with surfactant. So that is the goal, and again the aim is to barrier the barrier by external stimuli. So we are on course of that study. It is not I will not say it is concluding statement, it should be a concluding statement, but that is why we are searching for it. Okay.
So in order to acknowledgement, first I think these are appreciation or acknowledgement, whatever you say. But I think the first acknowledgement would have been the Department of Chemical Engineering, Calcutta University. So because it's pure the financial records. Yes, I can say that we have an output into process PA, and they discuss about whether we should go for our intake or go for a job. So then they said go for it. And so I should thank them for the first time. And we are using this Maharashtra Center at our institute. And eventually, of course, for the funding and for the solution as well, we are trying to build up a larger international science and group at our institution. So the other two members are Abhi Ghosh and Uday Ghosh. So we are working together between different problems, not in this one. These are again the part is one of the group picture. So she is Mona, is working on this problem. She is the group member. He is Pratik, Ayush, Raj, Preeti, Akansha, the tech at the time. And yes, so I thank all of them for their support, and they are going for hard work. And yes, so thank you all for your attention. So now, if you have a question, I would love to answer.
Any question on this presentation?
Yes, sir.
Please. Hello.
This one? This is? Distance is in the distance is in the reverse direction, right? So this is between the particle. Yes, surface and the particle.
If you look at the sphere, now it is the direction of the support is 0 point in this one.
Zero is here.
Zero is here.
Here.
Particle
is like that's what we draw in the reverse direction. So this is the path from the surface in the solution, and then we are slowly dragging to the surface. So surface is here.
it is presence of the nanoparticles.
The micelles, the presence of the micelles. Yes. Yes. Two micelles are on the side. So the goal was that can we deposit like what we aim is since we have this net charge between that micellar zone here. So this zone is negatively charged. So if we could push the particles to this point, then because of that. Like this charge density would be down to the surface. That was the expectation. So this charge distribution.
Yes.
Yes. So these two distances to be varied, but it was on the same level. Like the fluctuation, like this portion will be little bit very long. We are seeing that elongation of this part, the center part.
I have just one.
Yes.
I have just one query. You see, you are predicting only the growth mechanism.
Yes.
What about the shape, size, and the effect of vegetation? These three are also included in your mechanism understanding.
Okay, so we are really not, we are more bothered about that, what will be the growth rate. That is the first point we are trying to address. Then if the growth is, once you get the growth mechanism or the growth rate, then we can go for that, okay, what will be the, like how we are changing the surfactant concentration or whatever the other parameter conditions, then what will be the change? Like how it can, control the size of the nanoparticles or shape of the nanoparticles. So right now we are more concerned about that growth rate.
Okay, I think we have come to end of this session. There is no more presentation, I suppose. So I think we'll thank you all. Thank you all the participants for excellent time management. I'm sorry for the intervention for the second one, but anyway, that's a part of the life. And I also thank the audience for patient sharing, after particularly after post lunch. So thank you, everybody. Thank you.
Thank you so much for staying with us for a long time. Also to the best of trouble with this camera, sound, etc. So, now I would like to ask Rohini to hand over the to get this.
Center is again. Go to the center.
Likewise, yesterday we are not taking deep breath. Deep breath means we are not going outside from this hall. So he is not here today. Now we will continue because the other two lectures which we have, that will be online, and both the speakers are there. They are present online mode. So in this one, special chair that will be offline, and our alumni, one of our alumni, Mr. Bondupad, he also our alumni association executive member, and requesting and to take over the session. As this is here. Good afternoon. Last two sessions were details about energy to go through another very interesting topic. Let me first is from the content. Yeah, online. Hello, Sumant.
Hello, sir.
Just I will take few minutes to give a brief introduction of yours. Yeah. So one has completed his final examination from the firm. That is chemical engineering from Calcutta University 2009, followed by MTech from IIT Kanpur 2011. Then he joined Bhabha Center, Mumbai, as a scientific officer in 2011. I think since then you continue with the organization, yeah. And his current research interests include the plasma gasification technology for solid waste management and the plasma spray coating technology. I mean, both are very relevant and they when we are talking about like scientific domain. So let's we have to mention to Subhankar and let's see what he wants to convey to us. Subhankar?
Yes, sir. Good afternoon, everybody. Am I audible? Okay. And my screen is visible. My screen is visible to everyone.
Yes.
Okay. So I am Subhankar Bhandari from Bhabha Atomic Research Center. At the very beginning, I would like to express my sincere gratitude to organizing committee for giving me this unique opportunity to present my work in front of my respected teachers and gurus who has introduced me to this beautiful world of chemical engineering. So the title of presentation is Air Plasma Gasification Technology in Pursuit of Clean Environment. Basically, in this lecture, I'll be talking about advanced solid waste management technique, which is the need of the hour for our country as well as for the all over the world. So I have structured my presentation like this. I'll start my presentation by explaining the basic motivation behind this development, and I'll talk about air plasma gasification technology. Then I'll give a quick insight of the global and Indian scenario of this technology. Then I'll discuss about the air plasma torch developed by BRC, the challenges we faced, and how we have overcome these challenges. So all this journey I'll explain. Then I'll explain air plasma gasification facility in detail. I'll share some important facts and figures and the lesson learned during development and demonstration and operation of this gasification technology with various kind of solid waste. And finally, I conclude my lecture by highlighting the key points and take away messages. So now the basic motivation behind the development of air plasma technology, air plasma gasification technology, there are two aspects. First is our own in-house requirement of processing solid waste in BRC, and second is contribution for the society or the common public. See, if we make a list of all high priority societal challenges, then three names will come at the top. First is energy crisis, second is global warming and greenhouse gases emission related problem, and third is waste management. And interestingly, all these three major societal challenges are discussed in this forum since yesterday. So basically, we need a magic instrument which basically addresses all these three issues. So in this presentation, I'll elaborately discuss how a single technology, this air plasma gasification technology, eradicate all these three major global societal challenges simultaneously. So what is air plasma, right? The simplified definition of plasma is basically a high temperature ionized gas. Now, it is basically plasma jet is a beam of highly concentrated thermal energy having extremely high temperature. So, temperature is of the order of 8,000 degree to 10,000 degree Celsius, which is way above the temperature with the sun's surface, which is at sun's surface temperature is around 6,000 degree Celsius. So in plasma we can have as high as temperature like 10,000 degree Celsius. And another is
It consists of electrons, ions, and radicals and other excited species. So these two unique properties basically make the plasma unique, and it forces the other competing technology to take the backseat. Right? So air plasma gasification is basically a chemical reaction between carbon, hydrogen, and oxygen at high temperature. And in any chemical reaction, two things are important. One is kinetic, another is thermodynamic. So in plasma, both these kinetic and thermodynamics are in favor, because such a high temperature, so kinetic will be automatically favored. And since we have electrons, ions, and excited species, so the thermodynamic also will favor. So overall, it provides a superior thermochemical environment, not only for gasification, for any high temperature or chemical conversion. And this is the game-changing device. This is the device which produces the air plasma. You can see the jet length. So it's a concentrated beam of energy, and having the ions, electrons, and other excited species inside it. So this is the air plasma torch. In this picture, in the middle picture, you can see. Just let me enable my pointer. Yeah. So can you see my pointer here? So this is the air plasma, and here we introduce the iron rod. So when we introduce the iron rod in this air plasma, it immediately converted to liquid. It immediately melts. So because the temperature is way above the melting point of iron. So here we introduce the copper rod. There, the copper rod not only melt, it immediately converted to vapor. So you can understand the potential of the plasma jet. Here at the bottom picture, the paper board was kept. It was kept quite away from the plasma jet, but still it catches fire immediately, right? So these are the key features of the air plasma torch developed at VRC. To my knowledge, this air plasma torch is probably the first time developed in India in our institute, and it has some unique characteristics. Some of those, first one is it has a very long plasma jet. So the jet length is of the order of 300 mm. And it can produce very high plasma temperature, more than 8,000 degrees Celsius. It uses air which is freely available from the environment, and the airflow requirement is considerably low, only 30 LPM, and power is also low, only 30 kilowatt. So because of this property, it is very much affordable and very much attractive for the small scale industry. So this technology has already been transferred to industry, and you can see, you can find the details in our website. Now, what are the unique advantage of plasma over other conventional techniques? So the first one is, there are two buzzwords for this decade and upcoming decade. First one is circular economy, and second is decarbonization. So entire world is behind carbon-free energy source. So this is one example of it's a wonderful device for as a carbon-free energy source. We don't use any fossil fuels. So the carbon footprint in air plasma gasification is totally zero. Second is we don't use any fossil fuel, so we don't use a high amount of air. So air, because of the oxygen starved environment, the SOx and carbon dioxide, all these pollutants amount is low compared to other competing technology. And the third and most important is it does not allow the formation of dioxin and furan. dioxin and furan are very toxic element, and the permissible limit through the stack is only 0.1 nanogram per meter cube. So you can imagine such the toxicity of this. So because of this temperature, the temperature available inside the plasma gasification chamber, the dioxin and furan get disintegrated. It is well above is disintegration temperature of dioxin and furan. So above 800 degrees Celsius, dioxin and furan just disintegrate, and at the downstream we suddenly coils the off gases. So and dioxin and furan are forms basically 2200 to 600 degrees Celsius. So we have designed our system in such a way we don't experience this temperature. So in our system, dioxin and furan are not allowed to form. And because of the high temperature and these presence of excited species, the conversion efficiency is quite attractive. Whereas in competing in conventional incineration and all thermal processing techniques provides conversion efficiency of the order of 10 to 30%, where our bottom has found is in conventional technique is of the order of 10 to 30%. In our technique, bottom has only 1%. I'll show our result, then you can it will be clear to all of you. Conversion efficiency in our case, the solid waste to gases conversion is more than 95%. Okay, these two is really unique. First is the wide variety of solid waste we can process. There is no need of sorting. You can any kind of solid waste you just put into the reactor. The organic portion will be converted to value-added syngas, and the inorganic portion will be vitrified. Sometimes chalks need to be added, but the hazardous inorganic chemicals will be vitrified in this solid rock. It is called plasma rock, and it is totally non-leachable, chemically inert, mechanically strong, so it can be used for road construction. So it is clear to you that waste management is basically our headache. But plasma gasification technology not only address that waste management problem, but it also convert these waste into a valuable product. The organic portion will convert it to syngas, and the inorganic will be converted to this plasma rock, and it is commercial product, and it is environmental friendly, and it is certified by many environmental protection agencies that plasma rock is totally environmental friendly, and it can be used as a construction material. So why we need such a high temperature? See, in our childhood days or very ancient time, once upon a time, plastic was introduced to replace the cotton and all this to stop the tree cutting and all this, right? Now the trend is reversed. Now the plastic is banned and the cotton material is reintroduced. Now there are maybe multiple reasons for this. One reason is this. Why this thermal processing of plastic is banned is this dioxin and furan. As I mentioned before, it is said to be that one of the most toxic chemicals known to science. That you can imagine from its toxicity level, 0.1 nanogram per meter cube is the permissible limit. That is from the stack, which is 30-meter stack is very common. So at the height of 30 meter, 0.1 nanogram per meter cube is the allowable limit. But in plasma, this dioxin furan is simply disintegrated because in plasma chamber, plasma reactor, overall the average temperature is way above the disintegration temperature of dioxin furan. So, for thermal processing of plastic is the only technology available till date, to my knowledge. So, So this is the global scenario. The plasma gasification technology is spread all over the world, but most of them are in pilot or demonstration scale. The Westinghouse or alternate energy is the only technology which is successful, which makes the technology commercially proven at a bigger scale. They have planned at China, they have Japan, they have planned, and in India also they have planned. In Pune, they have planned to process hazardous waste using air plasma technology gasification, and the capacity is of the order of 70 ton per day. So this is the process flow. This is how the process flow diagram of air plasma gasification facility looks like. So it essentially consists of five components. First is the primary chamber, which is heart and soul of the primary plasma gasification technique. So this is where the actual waste processing occurs, and here this chamber can be utilized as a gasification or as an incinerator, depending on the air supply. So if we run in gasification mode, so more the thin gas will be produced over here from primary chamber, and then the thin gas will be combusted for say at the secondary chamber, and then then the off gases will be passed to the Venturi Coinchair cum Venturi chamber. This is very important equipment, important off gas processing equipment. It serves three purposes. First, it neutralizes all the acidic pollutant like SOx, NOx, HCl, and it removes the dust particle as well. Venturi is wonderful equipment for removing dust particle through wet scrubbing mode. And another is it coils the off gas from 1200 degrees Celsius to 100 degrees Celsius. So in doing that, we avoid the formation of dioxin and furan. In plasma chamber, dioxin and furan are disintegrated because of high temperature. But at the downstream, the precursor of dioxin and furan may get recombine and form dioxin at the downstream. With that possibility, we mitigate by quenching suddenly from 1200 degrees Celsius to 100 degrees Celsius. So after quencher from Venturi, we pass to a demister. We knock out here we use sodium hydroxide solution. So sodium hydroxide droplet is being knocked out by the demister, and then it is passed to the packed bed column where water is used as a scrubbing liquid. So all the residual water soluble gases are removed in the packed bed column, and finally it is released. The totally environmentally benign gas is released through 30-meter stack with the help of ID fan. So we have two facility at BRC. The left is the R&D facility. This is used for purely R&D purpose, torch development, testing of torch, testing of the reactor, and testing of this entire technology. And the right one is for regular operation. So here we process all the domestic waste produced inside the BRC campus. So you can see the conversion efficiency. So these the first experiment we did with this plasma gasification facility. So you can see there is no as such bottom as leftover. So conversion efficiency 99.7% we got at the first experiment, and we did experiment with various types of waste material, starting from simulated municipal solid waste, wet fabric, rubber gloves, kitchen waste, which contains lots of moisture, lots of water, and plastic waste, PATFT filter. These are the used filter. So in all the cases, we have achieved a very good conversion efficiency. And as far as the emission is concerned, the result is in front of you. You can see this is the flue gas result measured in the flue gas analyzer. Make is testo. So you can see the carbon monoxide 39, NO2 0, CO2 3.6%, SO2 is almost 0. And in the plant area, all the hazardous gases, toxic and flammable gases are not detectable. And you can see the emission release of steam through the stack. And you can see from this picture how vigorous the plasma gasification is, right? So this technology is being transferred to 7 industries till date. So here you can find the details of the in this website. You can find more details of this technology. And if anybody is interested to take this technology, you can approach our TDCD division through this website. And recently, we transferred this technology to a Kolkata-based company just 15 days back, and it was published in Times of India. So let me summarize the highlight points. See, the carbon-free energy source is the future, right? And a smart, integrated waste management technique is the need of the hour for the country as well as for the entire world, right? And it is the only solution for plastic for thermal processing. If we want to dispose the plastic through thermal processing technique, conversion efficiency is for wide variety of waste is more than 95%, and emission involved in this process are well below the limit prescribed by CPCB, and the waste to energy possibility is there. So I hope it is now understood that how a single technology can address all these three major global challenges: energy crisis, global pollution-related problem, and waste management. So this is let me quote let me read out a quote from US Environmental Protection Agency that one technology which potentially can use various types of waste, produce electricity and hydrogen without emitting dioxin and furan and mercury is plasma art technology. Municipalities can install a plasma art facility which will eliminate landfilling. So thank you very much for your kind attention.
No, jokes apart, it was a very relevant means particularly what is addressed. The transformation from carbon to gas. From the previous economy to the new economy where we're talking about waste about cycle of steam. Where the spread, but we are trying to build on the high conversion efficiency and very low. So most of the aspects. Still, I will request from the audience if there is a question. We can have
Yes, ma'am. We have tried electronic waste, and we did only one experiment and in that experiment we could recover. We used PCB, and by controlling the temperature, we successfully recovered the different components like aluminium, copper, and iron. So this is only one experiment we did, but this is feasible.
Okay, it is very promising, I think, for later course, because separation is a very problem for later course. By this transfer of technology, we can solve the
Yes, you are right, ma'am.
and electronic devices is a bigger problem now. After pandemic, we have faced many gadgets. So, we are talking about this year. I think you have to explore more electronic and plasma. Okay, thank you.
Yes. Sir, could you please repeat your question? I didn't get properly. Mercury, sir, we have not tried yet, but I think it's possible. People using this technology have used. Other people have used this technology, but I am not sure because we have not used so far.
Okay, so there are no more questions. So, thank you for your speech. And
Thank you, sir.
ready for it?
Yes, sir.
Okay. So we have a presentation before and one there. Dr. Devaji, he is the manager for the community. Ordnance Factory, Nalanda, Himachal Ministry of Defense. He has come to the PhD from his research is the development of ion-based materials biomedical and biochemical applications, including biosciences, drug development, and development. So, Allah is discussion is lost. You know the timing, so we go and discussion now.
Sir, is this screen is visible?
Visible.
Good evening, everybody. I'm honored to present a part of my PhD research study, development of electrochemical biosensor for measuring cholesterol, creatinine, and glucose separately and simultaneously. Different nanostructured electropolymers were grown over a metal nanoparticle dispersed graphene oxide based electrode and were used for testing glucose, creatinine, and cholesterol as the recognition element. These are the outlines of my talk. A brief introduction, materials and methodology used for developing different sensor electrodes, results and discussion, conclusions, and future scope. We all know biosensing techniques provide a fast and accurate measurement with high sensitivity and selectivity. However, challenges for developing a biosensor are also the same. That is to measure an analyte with high selectivity and sensitivity over wide linear range of concentration of an analyte with high reproducibility and low detection limit. The measurement time should be as low as possible. Among the different classes of biosensor, electrochemical sensor measures the analyte based on the interaction occurring between recognition element and substrate. That is the redox reaction happening between these two. Based on the recognition element used, this can broadly be classified into two categories: enzymatic or biomolecule based and non-enzymatic electrochemical sensor. The first category offers high accuracy and selectivity. However, tendency to be denatured in presence of toxic chemicals and with the change of temperature and pH is the main drawback of these expensive biomolecule based electrochemical sensors. To overcome these issues, nowadays scientists are developing different non-enzymatic recognition element for measuring different biomolecules and other compound electrochemically, because these are chemically stable, offers high reproducibility, and less expensive also. However, challenges for developing this sensor is to measure the analyte with high selectivity and high quantification limit. In this context, metal and metal oxide, organometallics, and polymers were successfully developed in different studies and reported with promising outcome. However, metal and metal oxide has a general tendency to measure a number of biomolecules over a very narrow range of potential, and therefore it is tough to segregate the responses from the measurement data for different biomolecules. Organometallics and polymers are easy to functionalize to make it selective towards the biomolecules and are found to be promising. Polymers can be developed by a number of ways, among which electropolymerization is easy to operate, requires small experimental scale, absence of toxic chemicals during the development, and are less expensive. Therefore, prime focus of this study is to grow polymethylene blue, polymethyl orange, and polyacryl amide over a metal nanoparticle dispersed carbon-based electrode to measure creatinine, cholesterol, and glucose separately and simultaneously. Before starting the study of the development of a system for measuring creatinine, cholesterol, and glucose using a single system separately and simultaneously, we carried out 3 different studies for checking the feasibility of the recognition element in measuring the glucose, cholesterol, and creatinine. Initially, polyacryl amide nanofilm were electrochemically grown over nickel nanoparticle dispersed graphene oxide based electrode and were tested for glucose measurement. This resistance of the electrode developed is approximately 585 ohm, which is much lesser than the other commonly available and stable electrode developed in different lab based on the polymers, and electroactive surface area is much more as compared to the other materials. It is approximately 6.22 square centimeter per square centimeter of geometrical surface area. It is further tested to determine the optimum condition for electropolymerization and for the measurement using differential pulse voltammetry. For the glucose sensor, it was observed that the scan cycle is approximately 60, scan rate is 50 millimoles per second, and others. It was then tested for selectivity, and it was observed that even at very low glucose concentration, the response observed is much higher than the response measured for other biomolecules at their very high concentration. The concentration reflected here is the double of their permissible biological limit. That is, for urea, the upper limit is 20 milligram per deciliter for human body. So here it was taken as 40 milligram per deciliter during the testing and during for measuring the sensitivity. And it was observed that after testing the sample in a clinical setup and synthetic setup, the sensor exhibited a wide linear range of, exhibited a high sensitivity and low detection limit over a wide linear range of glucose concentration. It was also to mention that polyacryl amide was electrochemically grown for the first time, and it was used for glucose recognition also for the first time. The high selectivity of the material towards glucose also confirms its clinical applicability, which was successfully tested in these studies also. Similarly, selectivity and electrochemical performance of polymethylene blue towards the cholesterol measurement was checked, and it was observed that the material is highly selective towards the cholesterol towards the creatinine. And similarly, polymethyl orange was developed and tested for measuring cholesterol electrochemically, and observed that the material is highly selective towards cholesterol. It was also observed that the material developed for creatinine sensing can measure the material over wide linear range of concentration, that is 0.5 to 900 nanogram per milliliter, and it can exhibit a very high sensitivity during the sensing. It was also confirmed that whether the material is applicable in other biological fluid like saliva, cerebrospinal fluid, and others during the testing for the testing of creatinine or not. And it was observed that this can be successfully applied for creatinine testing in these biological fluids also. For the cholesterol, for the sensor developed for cholesterol also, we observed the material and electrode showed a very high sensitivity, that is 226.3 microampere per millimolar, with a very low detection limit during the measurement of cholesterol. And this three study gives us an idea to develop a system for simultaneous measurement of cholesterol, creatinine, and glucose. How the electrode is developed? Initially, graphene oxide is prepared from graphite using Hammer's method. It is then sonicated in a nickel nitrate solution. Obviously, the concentration of nickel nitrate was optimized initially, and the metal loading was tested using atomic absorption spectroscopy. It was then dried, calcined, and reduced to prepare nickel nanoparticle dispersed reduced graphene oxide. The material is then dispersed in a polymeric suspension of phenol and melamine to prepare the NiRGOP electrode. The electrode is then segmented into three parts by engraving two pairs of microchannels over the surface of the electrode. Microchannels were engraved on the both surfaces of the electrode and engraved by laser ablation technique. Initially, the thickness of the width of the electrode were kept 11 millimeter. The diameter of the microchannel is approximately 200 nanometer, and the pair of microchannels were separated from each other by 0.6 millimeter. So four microchannels, actually pair of two microchannels, segmented the whole electrode into three parts. The three parts is then further used for developing different electropolymers over it: polymethylene blue, polymethyl orange, and polyacryl amide separately on each segment. For the during the electropolymerization, the other part were properly covered so that we can avoid the overlapping of one electropolymer to the others. These are the electropolymerization data captured during the cyclic voltammetry carried out for the electropolymerization using the monomer, that is polyacryl amide from acrylamide, polymethylene blue from methylene blue, and polymethyl orange from methyl orange. These are the ACM and EDX data measured for captured and measured for the prepared electrodes and sensor. These are the this is the inside of the microchannel we engraved at the surface. This is the smooth surface of the electrode developed in the study NiRGOP. These three are representing the formation of electropolymers at the surface of the electrode. The first one is representing the growth of polyacrylamide. Second one is the growth of polymethyl orange, and third one is the growth of polymethylene blue at the surface of the electrode. This is the TPR data. which was used to determine the reduction condition, and we observed that the entire NiO dispersed graphene oxide can be reduced around 550 degrees centigrade. Graphene oxide is around 200 degrees centigrade, and NiO is in between 450 to 550 degrees centigrade. So reduction temperature was maintained as 823 Kelvin during the reduction of the NiO dispersed graphene oxide for the preparation of nickel nanoparticle dispersed reduced graphene oxide. This is the FTIR data captured for measured for graphene oxide and reduced graphene oxide, which indicates the formation of reduced graphene oxide during the development of the material. The XRD data confirms the presence of Ni nanoparticle in the material, the presence of 111, the presence of 002, 200, the presence of 111, 200 and 220 planes of nickel nanoparticle confirms the presence of Ni nanoparticle in bulk FCC lattice inside the NiRGO film. The 002 plane observed near 26.65 degrees, 26.65 degree confirmed the presence of nickel nanoparticle in the material also. The Raman data measured for graphite, graphene oxide, reduced graphene oxide and NiRGO confirms the formation of NiRGO during the development. The ID by Ig ratio measured for NiRGO was observed to be much lesser than that of RGO and GO, which confirmed the successful reduction of graphene oxide. In fact, nickel oxide dispersed graphene oxide during the development of the study. It also confirms the electrocatalytic activity of catalytic activity of nickel nanoparticle in the reduced graphene oxide, in the formation of reduced graphene oxide. These are the FTIR data captured at the surface of the electrode and in the each segment of the prepared sensor electrode, which confirmed the formation of polyacryl amide at the surface of the electrode in segment A, in segment B formation of polymethyl orange, and in segment C polymethylene blue. It is then further tested in clinical sample for measuring the applicability of the material developed in this study for glucose, cholesterol and creatinine. It was observed that the measurement potential for cholesterol and creatinine are closer to each other, and due to that we faced some difficulties during the measurement of these three biomolecules simultaneously. However, no difficulties were almost observed during the measurement of biomolecules separately. These are the measurement data which confirms that the glucose can be measured using the prepared sensor over a range of 0.50 to 250 milligram per deciliter linearly, whereas creatinine can be measured over a range of 0.05 to 3.25 milligram per deciliter, and cholesterol can be measured over a range of 1.0 to 500 milligram per deciliter analyte concentration linearly. The sensitivity was also observed to be very high, and the correlation coefficient, the regression coefficient, was observed to be greater than 0.99, which suggested a better fit of the measurement data in this study. However, the problem was faced when we were measuring the biomolecules simultaneously, because creatinine and cholesterol have nearer nearer measurement potential during the measurement using the prepared sensor. The overlapping of the response was observed, and when we tested in when we tested the sensor in clinical sample, we observed this type of broadened peak, and the problem is it is quite tough to separate when operated at pH 7. However, we observe later on we observed that if we change the pH for the measurement, creatinine can be measured separately. In fact, by adding some suitable chemicals also, creatinine can be separated out. So by applying any of these two or both of these remedies, we can measure creatinine separately and cholesterol and glucose separately. In this method, in this way, we can measure the three biomolecules simultaneously using the same sensor electrode and the same electrochemical system. However, study is going on because this part is quite challenging, and one of my junior is carrying out this study right now. So with this, I wish to conclude the study. MAS has been fabricated successfully with three different recognition elements on a single substrate using microchannel engravement over the electrode surface. Microchannels were engraved at the surface using laser ablation technique. Polyacryl amide was used for glucose measurement for the first time and also developed for the first time using electrochemical technique. The prepared sensor showed promising responses in determining glucose, cholesterol, and creatinine when measured separately. Calibration data confirmed this prepared sensor can measure these biomolecules over a wide linear range of concentration, which also confirms its clinical applicability. The selectivity data also confirms the same. However, this sensor exhibits an abnormal response for creatinine when measured in a solution of pH 7 because of the nearer oxidation potential of creatinine and cholesterol in the experimental condition used, which can be overwhelmed by changing the pH or by adding a suitable creatinine active species or substances for measuring creatinine, or by using the both remedies. The present method and methodology may pave a new electrochemical biosensing platform for measuring different biomolecules simultaneously also. These are the future scope. Development of the multi-analyte non-enzymatic sensor for other biomolecules also possible using the same methods and methodologies. However, the electropolymers will be different and must be selective towards the target analyte. Otherwise, it was quite challenging for segregating the responses. Development of different environmentally sustainable electrochemical sensor for detecting other explosive materials. For example, clay-based electrochemical sensor for detecting dinitrotoluene, trinitrotoluene, nitrobenzene, and others for measuring different environmental pollutants and pesticides. Development of different multi-analyte sensor array for detecting different volatile metabolites of Mycobacterium tuberculosis. In fact, Mycobacterium tuberculosis, apart from methyl nicotinate, it releases 3 more metabolites, volatile matter, in fact, in huge quantity. So detecting any of these 4 or all of these 4 can help to measure the Mycobacterium tuberculosis, presence of Mycobacterium tuberculosis bacteria in human body fluids without using the sputum or other biological fluids. This can also be applicable for invasive testing also. So, thank you. Thank you, sir, very much. Okay, sir. Hello, sir. Hello.
Yes. Hello.
Hello.
Yes.
Yes, sir. Am I audible, sir? Hello.
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 Yes, sir. হ্যাঁ বলুন স্যার।
What is the advantage of your
স্যার অ্যাকচুয়ালি আওয়াজ খুব আস্তে আসছে।
Hello.
হ্যাঁ স্যার। হ্যাঁ স্যার।
What is the advantage of your
অফিসের আগে ঘোরাবে নাহলে ভিডিও করতে হবে তো।
over the existing method?
Sir, what is the advantage of?
Of using measuring creativity over the existing method? Currently, the method which has been used, what is the advantage of your method?
Hello.
What Sujita is asking, what is the advantage of your method? What is available in the market and what you are doing?
Can you hear me?
Available in market, we basically use different enzymes or other biological bodies. So these materials are generally used for 2 to 3 times, and sometimes these are use and throw method. Because these biomolecules or enzymes are generally degrading or denatured with the change in temperature, pH, and in presence of different chemical substances. However, when we tested the developed electrochemical structure using the electropolymer, we tested it for over 500 times, and we observed that the deviation in responses is lesser than 7%. So the repeatability of the material, repeatability of the measurement data is quite high, and so that recovery percentage is also high. So we can reuse the solution for other biomolecule measurement, and we can reuse the sensor electrode for measuring the other concentration in other solutions also. So this is helpful in both the way. The solution need not to be discarded because this can be used for measuring other biomolecules, and this sensor can be used over 500 times. So it is quite stable, and the cost is quite low as compared to conventional electrode or sensor available in market.
Thank you. There is no question. I think there is Thank you all.
Thank you, sir.
Thank you. The thank you.
Center.
We have reached the and we are closing this session here. Tomorrow we will be here again in the morning and the session will start at 8:30. In the morning session we have more lectures and the verification of the symposium and After lunch, we have presentation program for four batches of students who have passed from here. The latest is 25 years back, they have passed from this department. So for delegates, it is 10:30. For students and for me as well as some of our teachers, for those the time is 9:30. Okay, so we come here at 9:30. Okay, so we are closing this session here. And another is some students, those who have not taken the T-shirt yesterday, you may please contact. Talk to Arindam. Okay, he will give you those T-shirts.